So let me also start by acknowledging the organizers for the invitation and putting together this wonderful conference, very varied topics. So I am a theoretical condensed matter physicist, but what you are seeing there are 3 experimental images of fractals generated with these 3 different platforms. And I am going to tell you about that today. So for the ones who don't know, fractals are these beautiful structures that have the property of self-similarity. As you keep zooming in on them, you keep always seeing the same structure. The core curve is the structure of snow. The Mandelbrot set is the solution of a mathematical equation. And underneath, I show you a very simple mathematical fractal, the Sierpinski triangle. You start in 2 dimensions with the generation 0, and you cut an inverted triangle in the center. You remain with the 3 smaller ones. You cut again another inverted triangle, and you go on ad infinitum. And when you have cut so much, the system is no longer 2-dimensional, as the one you started with. It is also not 1-dimensional, like a line, but it has an intermediate dimension between 1 and 2. In the case of the Sierpinski triangle, the dimension is 1.58. It is defined as the log of the number divided by the log of the scaling. Let's see how this comes about. Suppose you start with a 1-dimensional red line. You scale it by 2. You ask how many copies of the red I need to cover the blue. The answer is number 2. You are in 1D. You start with the red square. Scale the dimension in the x and y directions by 2. How many of the red ones you need to cover the blue square? The answer is 4. You are in 2D. Start with the Sierpinski triangle in red. Scale it by 2 in the 2 directions. How many do you need to cover the new one? Only 3. So log 3 divided by log 2 gives you 158. So why should I care for fractals? Because they are everywhere. They are in nature. Romanesco broccoli, the structure of the roots, the structure of the branches, the structure of the leaves. They are inside our cells, our lungs, our circulatory system, our neuronal system. Our heartbeat is fractal. And it's very important that it's fractal. If it gets periodic or chaotic, we die. They are very important in technology because if you have a fractal, you can send and you can make an antenna. You can send and receive large and small frequencies simultaneously. If you make solar cells, you can store much more energy as you increase the complexity of your fractal on top of it. And of course, they are beautiful structures. You see here one from the 11th century, which is in Rome, in a church. Nobody knew what it was, but they were already building it because they are beautiful. The middle image is an Escher picture. As you approach the horizon, the structures get smaller. It has an underlying fractal structure. So now, if I think from a condensed matter perspective, the physics depends highly on the dimension. If I look at electrons in 3 dimensions, despite their interactions, they behave like non-interacting quasi-particles. When I come to 2 dimensions, if I apply a perpendicular magnetic field, the physics changes completely. I can get charge fractionalization in the presence of this perpendicular magnetic field, the fractional quantum Hall effect. If I come to 1 dimension, again, the physics changes completely. I can get spin charge separation, which is super nice. And everything changes depending on dimensionality. So the question is, what happens when I go to intermediate dimensions, to fractional dimensions? This is the question we have been already investigating for a few years. So I will try to show you very briefly the first part, which is when we built the first quantum fractal in the nanoscale with electrons. The second one is now simulations of the dynamics in a fractal using photonic waveguides. And the last one is a real material, bismuth, one single layer of bismuth on indium antimonite, which has now topological properties. Okay, so the first question, how do electrons behave at fractional dimensions? You will say, what the frac? Sander Kempkes was my PhD student who did the calculations, and Marlouis Lott was the one doing the measurements in Utrecht. This work is based on the pioneering work in the group of Don Eigler, when he first built the first quantum coral. So these spikes that you see in yellow and red are atoms of iron, and they are separated by 1 nanometer. And these beautiful waves that you see inside in blue are electron waves. It's the electronic wave function, what you are seeing down there. This is the smallest movie ever made. Each pixel is 1 atom. They did it for publicity for their work. But it took almost 20 years until someone decided to combine 2 quantum corals, open the door more or less to control the tunneling, to build molecular graphene. This was done in 2012 in the group of Hari Manoharan in Stanford. So this is the technique that we used to construct our first quantum coral. You see on the right the topographic images. Each of these dark spots is a little mountain. It's a carbon monoxide that's patterned on the surface of copper, and they confine the geometry, and then we can build the first 3 generations showing on top on the left. And what you see on the left underneath are the electronic positions in blue, in green, and in red. And I paint on different colors because they have different number of neighbors. So you are basically building dynamics of electrons in a lattice where the sites don't have the same connectivity and you don't have the same number of different A-B sublattices. So it's just a richer problem than what we are used to. So we build this, and we then have to calculate a very simple problem, Schrödinger equation in a fractal geometry. You know the height of the barriers, you know the size of the barriers, the radius and the height. It's very easy. And then we can also use a tight binding model to see whether the continuum and discrete descriptions match. Then you sit on the red, blue, and green sites. You take the GIGV spectra, you compare with the theory, and now you sit at 3 different energies, and you scan the entire sample with STM. And you see the images on the top. Underneath, you see the theory. Looks like we have built a Sierpinski triangle. On the left is the bonding, on the right is the anti-bonding configuration. But the important question is, do the electrons know that they are at fractional dimensions? Do they notice? Because I went only to the 3rd generation. I have a few cuts. Does this really mean I have a fractal? So for this, you take the peaks that you had in the local density of states. These are now in white and black. And you do a coverage of the white part. This is called Minkowski-Bulligand method or box counting method. You basically take a circle of a reasonable size compared to the surface you want to cover. You cover as well as you can, and then you count how many of these pink circles I have. 1, 2, 3, 4. And in a log-log plot, you plot the log of the number of circles compared to the log of the inverse radius. And you get a dot, the pink dot there. Now you reduce the size of your circle, you cover it all again, you count again, you get another dot. You keep doing it many times, reducing and increasing. And all your dots are on a straight line, and the slope of your straight line is the dimension of my object. And you get 159. So the electronic wave function is living in dimension 159. It knows it is a fractal. This is done for minus 300 MeV. You can do it for all the energies, and you see the red dots are around 1.6, well below the 2 dimensions when you have a square leg. Okay, so we can build fractals, which are not infinite generation, as mathematicians would tell us, just finite generation. And still the particles, the quantum particles there, know that they are at fractional dimensions. What about dynamics? Now I need to go to a different type of system. And for this, we are going to use waveguides. This was done in collaboration with the group of Shan Mingjin in Shanghai, and Xiaoyong Shu was the main experimentalist. I like to call this problem the quantum ant in the labyrinth, because in the 80s, Dejean and many others were studying a lot of fractals, but those were classical fractals. The question is now, when we look at quantum fractals, are there differences compared to what they have? Okay, so that's our fractals. We are going to build waveguides inside the chips using these femtosecond laser direct writing techniques. And the cross-section has the shape of a Sierpinski triangle. So each circle that you see there is one waveguide. These lines mean nothing. They are guided to the ice. And we are going to build hundreds of them with different lengths along the z-axis, because this determines time for you. And now we are going to inject photons on the top waveguide. They will propagate along the waveguide with the speed of light. And when they come out, you detect them. You divide the length by the speed of light, and you have time. That's why you need hundreds of them to partition time in many small steps. But at the same time, the photons will propagate along the transverse direction by quantum tunneling. And every time when you detect the exiting photon, you can take a photo, you take a snapshot. And then you can accompany the dynamics. We are going to investigate not only the Sierpinski gasket, but also the Sierpinski carpet. Now this is a square which has a hole in the middle. And if you take the little left square, you will see that when you scale it by 3 in the x and y directions, you get 8 copies. And now log 8 divided by log 3 is 189. In addition to that one, we also investigated the dual Sierpinski carpet, which now has dots where you had filled squares before. It's important because it has the same fractal dimension, but a different distribution of voids. So we investigate all these 3 structures, and now you see the photons. Now you can measure the mean square displacement, the variance, and plot it as a function of time, or propagation length in the transverse direction. You see that it started with an exponent 2.5. This is because I'm not starting in the center of a structure, but at the boundaries. It knows that the displacement is confined. And then at a certain point, 2.675, it deviates from the original value, 2.5. And you can see that 2.675 is when the light has found the first hole. And then it gets a bit confused. And at 3.875, it has picked up the fractal Hausdorff dimension. So it goes on like this until it has explored the entire fractal when it saturates. So the curve in red is the experimental curve, and the one in blue is a numerical simulation. What is very important here is that when it has entered the fractal regime, the exponent is the Hausdorff dimension, which is different from the classical prediction, which was a spectral dimension divided by Hausdorff dimension. So a quantum ant in the labyrinth is behaving differently than the classical ant. Okay, then we go to the Sierpinski carpet. We do the same, and we see it again. It starts with a 2.4 because now the confined geometry is a square. And when it finds the first hole, it picks up the dimension 189. It's amazing. Quantum particles can know the dimensionality of the entire structure after seeing one single hole. Okay, you do the same with the dual Sierpinski carpet, and now it starts with 189 because it's meeting the hole from the very beginning. So after we did that, I said, okay, what about the connection to the proposal by Roger Penrose that the quantum dynamics in the brain, the quantum propagation should be, the propagation of signals should be quantum. Well, this was a very polemic issue for very long, for 30 years by now. If someone would have told me that you could have quantum processes in the brain 30 years ago, I would have been completely, yeah, you would not believe it. Nowadays, I take it with a grain of salt. I tell you why. The same beautiful quantum Hall effect that Klaus von Klitzing has been measuring in 1980, and he needed to go to 1 Kelvin to see the plateaus, have now been seen in graphene at 300 Kelvin. So we are seeing quantum process at room temperature. You tell me, okay, but there was a magnetic field of 29 Tesla. You don't have this in your brain. Well, also on graphene, we have seen that when you deposit on surfaces, you form microbubbles, and these bubbles have a pseudo-magnetic field of 300 Tesla. And on top of it, nobody talked until now, topology may be extremely important. And carbon is very light. You don't have a strong spin-orbit coupling, but when you fold it and you form carbon nanotubes, you get a very sizable spin-orbit coupling. So it can very well be that topology is playing an important role. I am no longer dismissing it. And what I say here is we have now a very clear prediction about how quantum particles behave in this fractal. We know that the neuronal structure is fractal. It has been measured, its fractal dimension. We just need to compare. And then we know if it's classical or quantum. We had a quantum simulator for that. Okay. So there is an interview in the conversation if you want to look at that. Now, what about the real materials? Could we see topology in real fractals? So our colleagues in China, the group of Jingfeng Jia, has been growing bismuth on top of indium antimonide. And bismuthine is a very interesting object because from the first quantum Hall effect to see these beautiful plateaus, we needed high magnetic fields and low temperatures. With graphene, we could get rid of the low temperature, but we still needed high magnetic fields. Then we had the quantum spin Hall effect, which is an intrinsic property. You don't need magnetic fields, but it was still for mercury telluride. Lawrence Moll company needed to go to the millikelvin regime. But finally, Ralph Klassen, with bismuthine, he didn't need to have any magnetic field, and he didn't need any high temperature. He had the quantum spin Hall effect at room temperatures, driven by the strong spin-orbit coupling. So here, it's super nice because we can investigate topology in a system that has a very strong spin-orbit coupling. And maybe we get new candidates for Majoranas because we can get corner states in something that has fractal dimension and could bring lots of novelty. Okay, so this is our work investigating theoretically all what is there. They do an STM study along the boundaries of that second generation Sierpinski. You see underneath on the left that the substrate is insulating, and when you look at it, this turquoise peak there is a zero mode appearing at the boundaries of the sample. So we investigate now the effect of spin-orbit coupling in our theory, and we get all the phases that are being seen experimentally. We can understand them. There are edge modes at the outer boundary, at the inner boundary. There are corner modes around zero energy. Disorder is extremely important in the system. We investigate all kinds of disorder. The system gets amorphous, 40% disorder, and the edge modes and corner modes are resilient, so they are topological. Here is a type of disorder that could make us lose one of them underneath. Okay. So I come to my conclusions. I have been telling you how to look at systems at fractal dimensions. The first one, I have shown you that the electronic wave function fills the fractal dimension. I have shown you in the second one that if you look at dynamics in a fractal, there is a novel quantum regime that was not available before. I didn't tell you about the other ones. We have been studying calculus at fractional dimensions and discovered a time glass. You can also look at fractals in Hilbert space when you investigate quasicrystals. And more recently, underneath, you'll see an archive paper is the fractal Hubbard model, which allows us to have a metallic magnetic phase. As an outlook, we are building in Amsterdam a fractal lattice using optical tweezers to investigate strontium, which is now a Rydberg. I don't know how I'm doing with the time. I don't have time to show you this movie. Yeah? Okay. Then I can show you. It's a fun movie. So Einstein was saying that God does not play dice with the universe. And now I have my doubts. Build a triangle, choose a random point inside, and now we play dice. Up corner is 1, left corner is 2, third corner is 3, 4, 5, 6. Every time you play dice and you get a number, you connect your dot to that vertex and you choose the middle point. You go on playing dice hundreds of times, thousands of times, and you will see that out of this completely random game, a completely ordered structure, as we have in our brain, as we have in nature, emerges. So maybe God is playing dice with the universe. I would like to acknowledge my collaborators. You have seen already most of them. And I thank you for your attention. And I close by telling you that Feynman has been inviting us to construct matter in a bottom-up approach. And he told us that there is plenty of room at the bottom. But I believe there is even more in a fractal. Thank you very much.